First off, let me just say that today's talk is kind of something like a brainstorming session, in the sense that a lot of the ideas that I'm going to share are things that I'm really excited about and think could have potential. But they're all things that I've been kind of formulating over the past few weeks. And so I think there's also a lot of room for kind of improvement and fleshing things out. And that's kind of the motivation to share it, is that even though I'm excited about some of the ideas I have, I know for a fact that the best formulation of any of this is not going to come from my mind alone, and that the more kind of different perspectives I get, the better it'll be. Okay, so the basic idea that I want to present is to embed an annotated data provenance DAG in the data package.json file. I'm going to talk about why I think that's a useful thing to do, or it could be a useful thing, and how we might approach this, and then kind of what a future could look like with data repositories interacting with these. But just keep this in mind as like kind of the big picture of what I'm going to talk about, or to give you something to kind of work off of. The basic idea is, revolving around using some of the frictionless specs to encode the data provenance or data history. I think most of you are probably familiar with directed acyclic graphs, or DAGs, but just to be sure, briefly, DAGs are basically just directed networks that don't have cycles. Whenever you have a network, they can be undirected or directed. When you see an arrow, it means directed, so that the kind of movement goes in a specific direction and not back the other way. And a cycle just means that you can't do like A, C, D, and then up to B and back to A. So here, if you go down any path, you can't get back to where you started. And these are represented as sets of nodes and edges. Nodes you'll sometimes see referred to as vertices, and then edges as links. And there's some other terminology, but those are the common ones. Okay, I figured to kind of make it easier to get started, I would just start with a demo to give you a sense for what I'm thinking about. Again, the demo is very basic because it's all been done recently, but hopefully it'll give you a sense of what I'm imagining. So what this is, or what I'm about to show you, is just a React simple web app. And all it's doing is it's loading one of the data packages generated in this flow, and then kind of visualizing it. So the way I think about this kind of in terms of the end goals a lot is imagining what a dataset landing page could look like on a hypothetical kind of data repository. And so that's kind of what this is depicted as. And so what you're seeing is, for a single data package that represents kind of the end point of a data pipeline, you're seeing kind of what the landing page could look like. So on the left side, it'll be kind of typical information. This is all pulled from the metadata in the data package .json file, but just the data set ID, the title, kind of where it came from. Eventually, I want to encode things like the number of rows and some summary statistics that are generally useful. But for now, just like columns and version description. And then you can imagine including citations, and also download links would be a good thing to put here, linking out to something like Zenodo, perhaps. The middle is where views will go. And so this was actually one of the things I got really excited about this idea, is that, and this is something that Rufus actually, I think, has been thinking about much earlier, and I only just became kind of aware of, which is the idea of encoding views of data within the JSON files. And I think that's actually can be quite powerful. But this is just a view pulled directly from the data package file, and in this case showing a PCA plot for the data set, comparing the samples. And then finally, on the right side in the third column is the actual DAG. So here, right now, the nodes are labeled in terms of the actions, which should probably be changed so that the nodes would be, since they each represent like a stage of the data in the processing flow, they should be given a name like, initial, normalized, and so on. And then the edges should be the actions. But yeah, so download, reprocess, and collapse multi-entry genes. So this is a simple kind of data processing flow that I'm going to work with throughout this kind of today to share some of the ideas. So this is what gets rendered. So where is this actually coming from? So actually, I'll show you here. So what I did is I have a computational kind of pipeline set up using something called SnakeMake. SnakeMake is something that's pretty widely used in the bioinformatics community. It's kind of modeled after Makefile, but allows you to mix in Python and then call out to other things like R or Julia or whatever you want to. So it's a nice way to just stitch together lots of different components very kind of naturally. The goal is not to tie any of this to any specific kind of pipeline framework or programming language. So I'm trying to do everything as agnostically as possible, because I think the more important idea is not the technology, but kind of what's being conveyed. Okay, so the here you're seeing directories with outputted kind of stages of the data. The cache one's not important. That's just used for some of the libraries as it's downloading the data to cache kind of versions of it. But the three kind of stages in the pipeline are, actually here, start with the pipeline itself. So I mentioned there's a snake file that's kind of like a make file. All the important thing I'll just point out here is that the rules represent different stages of processing. And so the three stages are downloading the data, normalizing it, and then finalizing it. And then in each of these, generating kind of a data, a row and column metadata, and then a datapackage.json file. And so this is kind of one of the basic ideas, is that it would require adapting kind of computational pipelines to generate intermediate data packages representing each node in the DAG. And I think takes some extra work, but there's a benefit in that things become much more transparent and easily to convey. So what do those data packages actually look like? So if we go, oops, original. This one. So for those of you who work with data package, it should look pretty familiar. Nothing too exciting. The resources again are data, row metadata, and column metadata. Oops. And then here I have this kind of custom section where I'm adding some annotations that I think are generally useful for things like rendering in a web UI and kind of passing along to different pipeline components. But what's relevant for today's talk, or what's most relevant, is this section. So here there's a provenance block, and then within it there's kind of nodes and edges. In the original one, there's only a single node because this is kind of the starting point. And so it just encodes some information. It has an ID, describes what's been done, where it came from, and so on. And then the actual pipeline, or I wrote kind of a short API in R and in Python, and these will kind of embed their own tags of their versions, so you can keep track of that as well. And at the start, there's no edges. It's just a single node in the DAG. And then we can imagine looking at a later version of this. So that was the original one. Let's do the next step is normalized. And so I'm just printing out that provenance block now. And you can see the original node is here. This is what we saw before, just formatted a little differently. The second step is now added as a node, and now you have an edge going from the first one to the second one. And then you can do the same thing for the third step. Oops. Call the final, and then again, there's another node added and another edge added. And so that's kind of what gives us this simple DAG we're seeing here, where you go from download data to reprocess to collapse multi-entry. And again, as far as directed acyclic graphs go, this is not the most exciting. This is kind of a trivial case, but I think this will hopefully convey kind of some of what I think the potential is. Okay, so now with that kind of background, I think I'll continue with the presentation, and then we can kind of return to other aspects of the kind of actual code and metadata later. I think it'd be helpful first to talk a little bit about what kind of motivated me to think about this in the first place and why I got excited about it. So for those of you who happen to be here like a little over a year ago, I gave a presentation on a different but related idea, which was creatively named BioDat, and had basically had to do with kind of curating bio data and making it easier to integrate data by kind of standardizing some fields, adopting a metadata format within data package so that things would be conveyed in a very clear way, and then kind of building some modular pipeline components around that for exploratory data analysis, normalization, transformations, all those kinds of things that one would typically want to do. And yeah, again, the big motivation there, the original motivation was just to make it easier to integrate data sets. And if you go through the effort to curate data once, then you could kind of share it with other people and save them a lot of trouble to quickly pick it up and work with it. More recently, I've been realized that there's no reason to make this biospecific, and that a lot of the kind of ideas could easily be generalized and potentially benefit a wider community. And so I started to think about that and kind of work in that direction. And then, yeah, there's still like, even if there's this generalized kind of pipeline environment, there could still be domain-specific applications, because there are some things that you would only want to do with bio or genomics data or other types of data, and that's okay too. In this kind of project, I already was thinking about provenance and kind of encoding this in the metadata, but this was done in a linear form. So I had in kind of all the data sets I was processing and generating in this kind of framework, I had a provenance block with linear entries depicting each of the steps. So typically what would happen is the data set would get pulled. There's something called a recipe, which brings the data from some source into the kind of data package. And then it would get passed along to a series of pipelines to do different things. And then each of the pipelines would kind of tag or add its own kind of tag to the provenance section describing what the pipeline step was, maybe what parameters were used and things like that, and then when it was run and what versions. And this was, again, just to make it kind of more clear what exactly has happened to the data. But there's a problem, I mean, among other things, but this doesn't work so well when you imagine now having two data sets you combine into create a new one. This kind of linear form doesn't really capture that very well. And so this is where I started to think about how DAGs could be actually useful, not just for this kind of provenance in the metadata, but more generally just to accurately capture all the kind of details that go into a data processing flows. So yeah, DAGs are already used a ton in kind of data-oriented and software tasks. So one example is computational pipeline frameworks. So this is an example from SnakeMake, but many of the other pipeline frameworks, Luigi, Nextfloat, all very likely use similar kinds of data structures under the hood to handle dependencies of pipeline steps. And similarly, so package management and software management environments that kind of deal with dependency management, such as kind of Linux or homebrew package management. Conda is one that I use a lot that has package management that can be incredibly slow sometimes, but they're also dealing with a very challenging problem and do a lot of great work. So, but yeah, so DAGs are used in this case. The one that's probably excited me the most recently is the use of DAGs in causal inference and causal modeling. So causal modeling is basically an effort to kind of frame problems or think about kind of like science models before you even do any statistical modeling, to think about like, what are all your variables? How are they related to each other? And then try to consider alternative hypotheses and then explicitly depict these in a DAG form. So for instance, let's say you're interested, and this is just pulled from a recent paper in kind of pediatric studies, but if you're interested in kind of the impact of screen time on obesity, you could think about this kind of causal relationship here. But then, there might be other things that are kind of mediating this interaction, such as physical activity. So screen time affects physical activity, which in turn affects obesity. But then you can kind of, as you think about this more thoroughly, you can kind of imagine other ways that this kind of causal structure can play out. And so causal inference is kind of all about understanding these kinds of relationships and then using them to kind of constrict what statistical models you end up adopting and to try to inform kind of essentially what approach makes sense. And ultimately to incorporate rigorously causality into scientific modeling, which is not always the case. But what I think I really like about this, or what kind of excited me about this, is the fact that there's a big emphasis on making uncertainty explicit. So there's a lot of focus on things like missing data and confounders and kind of explicitly depicting those. And I think that's something that could be really useful to try to incorporate into data processing flows. So, okay, that said, here is the big picture of where I think this could go and why I found this exciting. So my premise is that we understand data far less than we think we do. What I mean by that is the current approach to data processing looks something like this. You start with some raw data and you process it and you get clean data. So this is typically done by someone referred to as an expert, be it a PhD student, a postdoc, or a data scientist. And then if you're considering this in the context of science, typically this would lead to a publication, hopefully maybe published to a data repository as well, instead of just like an Excel spreadsheet with the publication. And then, if you're fortunate, they'll also be thoughtful enough to put the raw data in the data repository as well. So there's kind of a more transparent record and empower people to kind of do the processing themselves. Whether people publish the code to do the data analysis with the publication, that's increasingly happening, but still quite uncommon overall, at least in a lot of the fields I've looked at. The bar is pretty low when it comes to publishing. Hopefully that'll change. But there's some problems with this. The big one that I think this whole effort could potentially assist with is that there's a whole lot of stuff that happens here that isn't really captured in a publication or even in the code that when you publish it. And what I mean by this is that data processing is kind of challenging and not obvious. There's no one way to like do it. That's always obvious, right? There's a lot of decisions that have to be made along the way, and often a lot of like weird and unexpected things that come up. And the people who work with the data and who have kind of training and understanding of the nature of the data, they'll make decisions, based on good reasoning and justifications, and sometimes some kind of exploratory analyses and things like that. That kind of decision making and even those kind of exploratory plots and things like that are seldom included in the publication or published in some kind of public and transparent way. And so that kind of knowledge gets lost, and we just end up seeing the clean data and we kind of forget all the assumptions and things that went into it. So yeah, what we get at the end of the day is not so much the best way to process or analyze some data set, which is kind of what we think of when we think of like clean data, but instead what we get really is what one person with their own particular perspective, skill set, understanding, reasoning, and so on thought was the best way to process the data. Just to elaborate a little more on the problems, experts are humans with limited knowledge and specific experiences. So, I consider myself to be quite knowledgeable in the kinds of data that I work with, and I at least try to put in a lot of time to understand things and read and, test my knowledge. But still, there's a lot I don't know. And so my own kind of interpretation of it is going to be biased on just the experiences and kind of what I do know. I think the framing and expectation that there is a single best version of the data is wrong. So this is, again, like thinking in the context of science, where you often have an advisor that hands some kind of raw data off to a student and says, process this so we can answer this question. There's kind of this implicit assumption that there is a way to process the data optimally. And I think that's just not really a great way to frame it. And that really, there's potentially many different ways you could try to process data to answer different questions that are all potentially useful. Data processing and analysis is like an art. So like I said, there's just a lot of decisions that typically get made along the way that there's no obvious right or wrong choice. If you were to give the same raw data to 10 experts, I think very often you would end up getting 10 different results back. And then, yeah, again, a lot of information is lost when you just present this kind of static slice of the clean data at the end. Context, assumptions, reasoning, and so on. And then finally, so I think one of the big problems in all of this is, again, that not always, but very often you have individuals who are going through this process, right? There certainly are cases where there are companies who have teams of people who sit down and collectively try to work through these problems together. But very often it's something more like an advisor handing a data set off to their student or postdoc, or even in companies, you have someone who's paid, they're hired as a data scientist or a data engineer or whatever, and they're given some data set and some problem and kind of expected to just know how to do it themselves or figure it out. And when you do have multiple people working together to analyze the same data set, unfortunately, it tends to be done independently. So I'm thinking of examples where there might be some kind of high quality data set that's published online, that was collected by multiple institutions and costs a lot of money. And then you have lots of individuals in different universities and companies and whatever downloading the data and then independently trying to go through the same processing and spending many, many hours coming and each kind of ending up with their own interpretation of it. So yeah, there's a lot of redundancy and just kind of lost missing shared insights, I would say. It's kind of related to problems in science publishing and kind of the static nature of that, but we'll save that for another day. Okay, so what I think would be a better approach, and where I think this whole kind of idea of encoding the data processing flow into DAG could be a step in the right direction, is it would be good to shift from this focus on the single static data sets, the kind of processed or clean version, to thinking of it more like a collaborative, evolving data workflow. So the initial data processing attempt you treat more like a first stab. So even if you're doing it on your own, you kind of publish it, on GitHub or out in the open, and then other people could come and kind of improve on it. So basically, if there is data that there's more than just one person who cares about that data, which is often the case, I think there is a community that is interested in different types of data, then they can kind of collectively work on it and kind of iteratively improve the processing of the data. And then the big kind of motivation or intuition is that the more perspectives we can involve in the data processing flow and understanding the decisions being made at each step, the better chance we have of ultimately understanding the data in the end. So the DataDag, which again is just kind of a tentative name I'm using to refer to this idea, but why I think it's useful is because I think it could be a potential mechanism through which this kind of collaboration could take place. And it's an effort to make all the assumptions, reasoning, uncertainty that goes into data processing much more explicit and transparent, so that we have a better understanding not only of what we think we know, which is kind of the emphasis in science publishing. You kind of take this whole messy data processing flow and you distill it out and kind of sweep a lot of the uncertainty under the rug and present this nice, like, clean linear story. That's our understanding. But I think as important, or maybe even more important sometimes, is it would be good to know just how much we don't know and how much uncertainty is going into this data processing flow, and just make it more obvious. So the basic idea, encode the data provenance into DAG and the metadata. For each step in the data processing workflow, you take the previous DAG, read it in, and then add a node and an edge. It's pretty straightforward. I would try and have already started, but basically create APIs in different languages to facilitate this process of kind of reading the DAG and updating it and kind of working with the data packages. Each node in the DAG represents a data set at a particular stage of processing. And then each node can be associated with one or more of the following. So annotations, which could be markdown notes on processing logic, assumptions, caveats, and so on. So these are the kinds of things, if you think about like as you are analyzing data yourself, you might kind of notice some things with the data like outliers or just have questions about it. And you might keep a note of that to yourself somewhere, or maybe write a comment in the code. But I think those are the kinds of things like this kind of interpretation that's going on and that doesn't really get included in the publication necessarily are still really useful to try to capture. Because often, like, the people who are working with the data, they have these questions and they have these ideas for good reasons. So it would be good to kind of save these and allow other people to use them and kind of get a grasp of how people are thinking about the data. The other thing that could be incorporated and associated with each node are one or more views. And so views in this case refers to just plots that are encoded in Vega-Lite JSON. And this could be used to basically like motivate this reasoning. So as you imagine kind of processing the data and taking it from stage A to B to C and so on, often you're transforming the data or filtering the data or modifying it for a particular reason. And more than just, write a sentence in the paper saying we normalize it this way, it'd be nice to say, we normalize it this way. Here's a visualization of it before and after, and kind of this is why. Or in cases where there's like outliers that you're filtering out or things like that you're dealing with, you could actually visualize those explicitly and encode this in the data processing flow so that someone else could pick up this kind of data package and see like, oh yeah, this is what the user was referring to when they made this decision to filter, and that makes sense, or it doesn't make sense. So data packages would be generated associated with each node, and I'll talk about a variation of this idea towards the end that I think is also interesting to think about. But for now, just assume that, yeah, each node is associated with a separate data package that includes the data for that node, and then kind of the DAG representing everything that came before it. And then finally, it'll be useful to have a web UI that can read the metadata and then render the DAG and some other stuff. And that's kind of what I showed you in the demo earlier in a very simple form. So what that overall process could look like in practice, you would have a GitHub repo with your pipeline. So here in this kind of toy example, there's only 2 steps in the pipeline. The first one and second one each have a separate script associated with them. You could have an annotation, a markdown file essentially with notes depicting kind of decision making and just things to look out for in each of these steps. And then finally, you could have different types of views that you incorporate with each of the steps as well. And a recipe.json file is just some metadata that would include that would facilitate any kind of tooling to understand and generate these DAGs. I can maybe share that later. But yeah, so this would get run and would generate data, 2 data packages in this case, which can then be published to Zenodo. And then finally, you could imagine having a web UI, which can kind of load these JSON files, and you don't even need the data, which is one of the nice things. Like, especially in this case, I mean, the PCA plot data is separate from the data package, so you would have to pull that. But if you're generating views like this, it's potentially small enough where you could even embed the data for the views directly in the data package so that you'd have a single file that could be read by like a web UI or command line UI or whatever, and then kind of lots of useful things pulled from it. Okay, so one of the big questions that I've been thinking about is, should the data package represent a single data set or kind of all stages? So initially, as I was thinking about this and kind of what I've described thus far, the kind of focus is on single processing stage, which is that the data package that you look at only includes the data for a single stage of the processing. It still includes the DAG for all the steps leading up to it. And then also the views and annotations are kind of limited to the current stage of processing. So if you're imagining looking at the final version of the data or whatever, you would have the final version of the data, the annotations and views for that specific stage, and then you'd have kind of a DAG just referencing the IDs of all the stages that came before it and kind of some basic metadata. But what you wouldn't have is the data for the previous steps, and you wouldn't have the views and annotations for the previous steps. There are other ways you could think about framing this that could potentially be useful. Another one is to basically start from this point, but then in addition to including the kind of the DAG and the metadata, also include the views and the annotations for all nodes. The motivation here being that, typically the annotations and views, are marked down in kind of JSON. They're not very large, so the cost of including them would be quite small overall. And the result is that if someone downloads the final form of the data, they would have not just kind of the data and annotations and views associated with that stage of processing, but they would have kind of the kind of visualizations associated with all and the kind of reasoning associated with all the previous steps. So I think that's potentially useful. It's still lightweight. And then, yeah, you could essentially pull the actual data for other stages in the DAG as needed or as desired. And then finally, there's kind of a third version of this, which is same thing, but then include the data as well. So views, annotations, and data. And this is probably only practical for smaller data sets, because if you have a large kind of data processing pipeline, you might have many stages, and then, collectively the data sets would all add up to a lot and be kind of bulky to pass around. But in reality, I mean, there are some data sets that are really small. And the nice thing about this is that it's portable and self-documenting, so that you'd have a single data package that represents the data at every stage in processing and kind of all the decision-making and logic that went into each of the stages, kind of visual, EDA, and so on. So it's highly portable and self-documenting. Okay, limitations overall, these are just a few examples, but first one is bookkeeping. It takes some effort to kind of modify pipeline codes to read in the DAG and update it and then write it back out. I don't think this is that bad, to be honest, just in my own experience of working on, trying to move my pipelines over to this framework already. And I think there's room for some kind of libraries to assist in this process and make it even easier for users to kind of generate and update the DAG. But it's something to think about. So far, the focus is on tabular data. I think ultimately it's interesting to think about other types of data and how this could be used for that. But at least initially, I'm just, focusing on a simple case of tabular data. And then there's a question of scalability. So, I mean, I've showed toy examples with just a few stages, and it's easy to visualize. In moderate data processing flow, where you might have, a handful or tens of steps, I think the DAG depiction could work fine. When you start to get to much, much larger data processing flows and think about like how to visualize that, it becomes a little trickier. And then if you think about some of the other ideas I'll talk about in a moment, where you might imagine like forking the DAGs and creating alternate versions, and then how you depict the relationship between them, it could also become challenging. But I don't think any of these are kind of showstoppers per se, just things to be aware of. Okay, and then one of the last things I want to talk about is basically an idea for where this could go in the future and what I think is exciting. So one of the ones that I alluded to earlier on when I was talking about kind of causal inference is this idea of visualizing uncertainty. So I think maybe for, I'll pull up the webpage again in a moment, but actually, I'll do it now. So here's a DAG. Right now, the nodes are only being colored to highlight kind of what's currently visualized. So this is kind of the node that's being depicted here in terms of the views and metadata and so on. Eventually, one would ideally you want to make this navigable, so you could click on the different nodes and go to the dataset landing page at the different stages of processing. But you could also imagine encoding other types of information in this DAG, right? So like for visualizing uncertainty, for instance, you could imagine changing the color or opacity of each of the nodes in proportion to the amount of missing data or imputed data to kind of transparently indicate where those are and how it's changing across the data processing flow. So encoding other types of information, you could also imagine like essentially having different colors assigned to different types of operations. So like filtering, or if you have operations that are kind of more continuous or discrete in how they're interacting with the data. One could imagine conveying the variance of the data as it changes across the data processing flow, because this is something sometimes we'll transform the data in a way thinking it's helping us, and we end up, losing a lot of the information or the variance in the data. And I think if you were to kind of visualize, color all the nodes by variance, or have the option to kind of toggle between these different layers of information, then one could kind of see much more clearly. It could also be interesting to think about like, demographic information. So for instance, in a lot of the genomics data that I work with, there's kind of the goals are to develop treatments to help the population, right? And so the population is very diverse. The data sets that are used are often not. And I think making that much more transparent can be a good thing. And then also, if you have like filtering steps where you're removing, patients or observations from the data, it would be good to know if you're removing things in a biased way such that you're affecting certain populations more than other. Okay, and then last couple things. If you were to imagine having, so the whole motivation again for all this is that by encoding all this in the metadata file, you could put all this on GitHub, right? So the data pipeline could go on GitHub, but also the generated, the metadata files could go on GitHub. And then someone could essentially fork the repo and then create their own variations of it if they disagree with you. And then if you would imagine a repository that interfaces with kind of different versions of a data processing flow, you could think about users essentially voting on which versions of it they think are the most useful, or voting on different steps within a single processing flow, or voting on different views and so on. I think there's a lot of potential there. If you've ever used Kaggle, they have something called Kaggle code. It used to be Kaggle kernels, but it's basically just a way that for the prepackaged data sets that they have, people can submit notebooks, and then the community can vote on which notebooks are the most useful. And I think that's incredibly useful and missing from pretty much everywhere else in science. If you have data that's now in this kind of nice data package format where someone could download it and very easily start working with it, it would be really useful to provide a means where they could share basically their own explorations of the data and point out interesting things they're finding in a format like a notebook or a data sketch. And I think for time, I'll just skip this, but it's also interesting to think about. So this is using the DAG in one way. One could think about kind of recursing in either direction and think about like if you have, if you have different kind of forked versions of it, you could depict those kind of different versions as a DAG, so a DAG of the DAGs. And then you could go inside as well and think about each node is a data set. It represents a collection of variables, and then you could think about like depicting the relationship between those variables using a causal model or probabilistic graphical model. And that's pretty much it.